All right. Yeah. So yeah, as Marta said, I'm working on the JUNO detector alongside Marta. So I appreciate the invitation. And yeah, JUNO's a neutrino detector, hopefully filling with water actually really quite soon. So this is talking about work done, a couple of years ago in preparing a core collapse supernova alert system, which is now, as we're commissioning the detector, is fiercely being tested alongside all the different components of the detector. So yeah, hopefully entering into an exciting time. But yeah, I'll just get started. So yeah, neutrinos, we've been detecting them for a while, about 70 years or so and really covering quite a large energy range. From the first reactor neutrino detection, or the first neutrino detection about 70 years ago. But then, obviously most recent particle physics Nobel Prizes, solar neutrinos from SNO. And then obviously Super Kamiokande, higher energy atmospheric neutrinos. And then recently in the past decade or so, really stepping into these really high energy, low flux um, cosmological neutrino sources in really supermassive neutrino detectors. But yeah, right in the middle there, energy wise, are say supernova neutrinos. And yeah, I guess we're eagerly waiting our next chance to measure those since 1987. So yeah, maybe I'm preaching to the choir in some cases, but yeah, just a little reminder, what we do have so far is a handful of events over about 10, a 10-second burst, generally high energies in the low energy scale of things. When we talk about neutrino detectors, we had an approximate direction from Kamiokande, and we saw them hours before the optical signal. So yeah, how was this done? It was across three detectors against Kamiokande, IMB, and then also Baksan. So yeah, a lot of excitement and so on, and yeah, eagerly waiting the next one. So yeah, we've obviously, this is in 1987. We've come a long way in terms of neutrino detection. I mean, things are just tend to get bigger, larger, and more precise. And this is kind of true across all energy ranges. So just talking about some soon upcoming detectors, obviously JUNO, which I'm focused on today, covering say MeV and say hopefully goes down to tens of keV in energy. And then obviously we know Hyper Kamiokande and Dune, say covering some higher energies, and these detectors are really getting quite enormous. So we'd like to see what we could do with them in terms of supernova neutrinos, and then obviously in the highest energy side of things like IceCube, but there's certainly other future neutrino telescopes being planned and built out there as well. Um, yeah, so I've attended enough seminars to know I can't really cover all the, things that people want to test in terms of another measurement of supernova, but just in general, understanding their mechanisms and so on. And then because they're quite extreme environments, obviously there's a large number of new physics we'd like to test with these events. But as you say, we want to be prepared for the next one. So we have a lot of new, fancy, massive detectors at hand. So what can we do in terms of, collecting statistics, measuring their energy, their timing, their direction, and then some flavor sensitivity as well. And then when it comes to neutrinos specifically, we know they come early. So we really want to be sure that we were maximizing our use of them and, alert the rest of the world and use every tool that we have to measure these upcoming events. So yeah, like I said, the thing that makes neutrinos so annoying to detect, and we have to build these big expensive detectors, uh, is useful in the way of astronomy in that they, travel in super long, unperturbed paths, and you can really probe deeply into the sources of where they're accelerated within. So yeah, we want to use these to our advantage, obviously, and give us fast and confident warnings. Try and reach as far reaching as we can. Obviously, this is difficult because you need a very large detector, and in some ways we are limited in that case. But then, once we see the supernova, what can you learn about the supernova that are produced, say, deep within these massive objects? So what do we want to measure with these neutrinos of all flavors? where did they come from in the sky, their timing evolution, and then also say their absolute arrival times, useful if you want to compare between different detectors and so on. Measure their energy spectrum. You can kind of define that with your energy resolution, and then also say what energy range are you covering, and then all neutrino flavors. So just an approximate, categories of what we want to measure. So generally, these detectors are so big and expensive, they're not built specifically to detect, say, a rare transient event. They're generally built for other physics, and supernovas often thought as maybe a secondary function. But there's plenty of neutrino physics going on. So what tools do we have on Earth to make these measurements? So water Cherenkov has been around for ages. I just use Super K. This is not exhaustive list, but Super K is an example. Say soon to be Hyper K, hopefully. So yeah, they can do direction measurements. You can measure their timing evolution, collecting enough events, and so on. You can measure their energy spectrum, to some degree of resolution, but obviously with the Cherenkov light, you cannot go to, say, super low energies. And then you can measure, say, electron neutrinos and then neutral current scatterings as well. So in some way, you're sensitive to the different flavors. When you consider, say, really massive water, Cherenkov or ice cube came through net, for example, right now, Baikal GBD, and then in the future, there's a lot of future neutrino telescopes being planned. This is more on kind of like the single optical module level detection. So you can't really do some pointing or energy spectrum or different flavors, but with the statistics you have in a detector that size, you can certainly do timing measurements and obviously absolute time as well, which is quite useful. Liquid argon detectors, obviously Dune coming up. It's kind of super well-rounded. You can do pointing, timing, energy, and all flavors. I guess somewhat say you can't reach, say, the lowest energies if we're comparing to, say, other detectors, but super well-rounded. Dark matter detectors, these are intended to measure dark matter, but obviously they're getting good at measuring neutrinos, and they do quite well, and obviously you can reach super, super low energies. And then, yeah, today I'm just going to be focused on, say, liquid scintillator detectors, namely JUNO, but you can look at, say, other studies being done in all these options we have for detection, and obviously that's why we're here today in a SNEWS seminar. Okay, JUNO, introduce you to the experiment and so on, and then specifically talk about the alert system and then maybe its expected performance. Okay, JUNO, it's in the south of China. It's buried deep in a mountain. You can access it through a slope tunnel, which is quite fun, but realistically, everything's kind of goes down the vertical shaft. And it's big, I'm working on the experiment, but sometimes you forget how big it is. This guy had the same reaction I did when I saw it, so I threw him in there. But yeah, it's a big, the biggest of its kind, a liquid scintillator detector. Yeah, so its main goal, clearly, it was built for the goal of, say, determining or measuring the neutrino mass ordering. And so it is primarily a reactor anti-neutrino experiment. Very, very carefully placed 53 kilometers from two different reactors, placed exactly in this optimal distance to measure oscillation. So its primary objective is to measure antineutrinos from reactors. Obviously, supernova produce antineutrinos, so say reactors are a sort of background, but this is what it was built for. So you just have to work around this fact. Yeah, and so basically it wants to measure to kind of an unprecedented level of resolution the oscillations in the reactor spectrum. And so to do that, you need a very good reconstruction or energy resolution to reconstruct these very small, subtle wiggles in the energy spectrum. And then from that, you hope to separate normal ordering versus inverted ordering, and then also get very, very precise measurements of, say, the other oscillation parameters. So to achieve this is the detector itself. It's about 700 meters underground. And so you have this very massive acrylic vessel. This is a photo taken earlier, but actually now the acrylic vessel is sealed and completed. And it's filled with about 20 kilotons of liquid scintillator. It's been watched by, a lot of PMTs, big and small, 20-inch ones, 3-inch ones as well, filling the gaps. And then on outside, you have a water kind of, what do you call, shielding and veto for muons. And then not only beyond that, some outward facing PMTs, you have to a limited extent coverage from say this top tracker, and that's used for reconstructing muons. So it's not super deep. There's actually a measurable kind of significant background of muons, and this will come in later for detecting supernova as a primary background. And so this veto strategy has to be, clearly worked on and optimized to make sure that we're removing the right amounts of data. And actually, there's plans to put extra PMTs. We have spare PMTs to fill the pool outwards. So hopefully boost the vetoing, which is already quite high, but it can always be improved and be made perfect. So just to compare with, say, other example liquid scintillator detectors, I mean, there's maybe too much noise in this table here, but just to look at obviously the size, the coverage is the highest of its kind. And if you want this super high energy resolution, you need super high light collection. And that's exactly what is being pushed for to say, reach this 3% energy resolution that we would like to be able to separate normal and inverted mass orderings in neutrinos. Okay, that's the main goal, but obviously we're here to talk about core collapse supernova. There's all different flavors that come through the detector, and so you have different detection channels, IBD, proton elastic scattering, electron elastic scattering. You have some interactions with carbon because you have a liquid scintillator which contains a lot of carbon, producing some higher energy events. And say just to get some numbers from a study done earlier, say your typical expected supernova at 10 kiloparsec. These are the kind of event statistics you expect to collect inside the detector. And so, and there's questions, when you have when you can reach a very low energy. We've seen a measurement from the Panda X dark matter detector of sevens scattering from solar neutrinos. So we wonder, can we also measure those in a supernova if we can reach low enough energies, though obviously challenging. Yeah, so this work's going to just focus on, say, the golden channel. I mean, the JUNO is an anti-neutrino detector primarily. So we're going to talk about these highest energies, tens of MeV anti-neutrinos from supernova. And so already, at high energies, you have very low backgrounds. And then when you add the fact that it's a coincidence event, you can get to, let's say almost zero backgrounds in some ways with a coincidence search. So it's kind of designed for these types of events. But just to say, this focuses on the higher energy sort of things. But if we do see a supernova, currently the plan is that we will, save, say, minutes of triggerless data. So we can save all energy events and then we can later analyze them. But in terms of coming up with alerts, IBDs are certainly the way to go. Okay, so the alert system or systems, just a kind of overview, and you can obviously see more information here. We're considering, say, not only the supernova burst, but also neutrinos emitted before the burst. So these are lower fluxes. We'll come into it later, but considering both, say, processes, evolutions in the supernova. Obviously, there's a bunch of models out there, so you have to test a few, and again, we'll cover these later. Consider the impact of mass ordering, the assumed mass ordering that we obviously hope to measure with reactors, but then also could you do it with supernova? Consider a few different progenitor masses. Also evaluate pointing in JUNO, a liquid scintillator detector. And then we have a few alert systems, which I'll come back to later. So the prompt monitor is a sort of fast, low resolution, trying to get as quick an alert as possible. But then we also have other monitors for, say, as I said, the pre-supernova, and then also, say, maybe a slower but more careful monitor as well, using, say, full event reconstruction when you take a little bit more time to, say, sift through the events. And all of these are evaluated versus potential supernova distance from Earth. Okay, so just to talk about pre and post, so we're aware of, say, the supernova burst. It's about tens of MeV. occurs over around 10 seconds, and we assume these models, Garking and Nakazato, and this is, say, the rate of events you'd expect at JUNO, 10 kiloparsecs, covering, say, about 10 seconds. And then pre-supernova is a much lower flux. It's a bit lower energy, orders of MeV. But this flux, say, rises in about a day before the collapse. So this is, if you can measure them, that would be, extremely good. But you kind of have to get lucky, or hope that the supernova is close enough that we could see them. So this would be that kind of gradual rise of the IBD rate, say, hours before the collapse. Yeah, it is very faint. You have to be lucky. Also, there's information there in terms of you have a large suppression expected if you have, say, inverted ordering and so on. But anyway, if we can measure that, that's great. And so if JUNO has the capability, you better make sure you're prepared for that and hope you get lucky. Okay, so again, pre-supernova, quite close to Earth, supernova at 10 kiloparsecs. These are the kind of energies, these are the kind of neutrinos you expect. Then you have to pass them through your detector response. Obviously, it's very good energy resolution, but when you consider, proton scatterings and account for their quenching and so on, these are the kind of energy spectra you expect. And again, I'm mainly going to be focusing on the blue curves here, the higher energy IBDs here. But obviously, we're working on, and hopefully there's studies in the future considering, say, the full energy spectrum, and also what you can do with this full energy spectrum once you've collected the events. But here is mainly focusing on the alert side of things. Okay, signal and backgrounds. Again, just to cover, we're mainly focusing on IBDs from the supernova, tens of MeV. So IBDs you have to consider from reactors. Our signal generally, but it's a background here. Atmospheric muons, it's a relatively high rate, and these produce, we're looking for high energy events, so they produce bright events that light up the detector. So you have to remove those. Also, they can produce, say, spallation products, follower events. There's kind of a lot of different types of events, but they look like IBD events. So you also have to remove those. And this is specifically a problem for supernova. So supernova, you're looking for a burst of events. The other events here, backgrounds I'm saying are relatively constant, but muons can come in clusters, and so if they cluster like a supernova event, they're particularly dangerous. So you have to be very careful in removing those. And then radioactivity, if you want to go to lower energies, you do have to consider, but anything above 5, say, approximately, you're kind of safe. Okay, just to remind that there are 3 systems here, and unfortunately I'm going to be swapping between them. So this is a little cheat sheet. When I'm talking about the supernova, the higher flux of events, and I'm talking about the prompt alert, I just mean higher energies, very fast in analysis, nothing too in-depth there, just searching for high energy events. Then you have the more careful online monitor where you take your time to analyze things. And again, that's the supernova event. And then the pre-supernova event is say lower energies. And because it occurs over hours, you do have time to, say, analyze things more carefully. So just this will be in the top right corner, and hopefully reminding which one you're looking at. Okay, so first, supernova, prompt, quick and dirty, high energy. We do not have time to reconstruct, so we just consider, say, the total number of hits in our detector is approximately the energy. And so this is N hits on the y-axis, and then your energy deposited in the detector. And so the gray lines are, say, some energy cuts. So we remove, say, the lowest energies and remove the highest energies, and look in this band here. So if you look on the right plot, you can see this is N hits. So the blue is the signal from supernova neutrinos, and then backgrounds would be your muons, which cover, all over the N hits range. And so they're particularly dangerous, but we're trying to avoid the reactor antineutrinos, and we're trying to avoid the follower events. So a muon comes in and produce some spallation products. We want to avoid those. So this is the reason for these N hits cuts. And this is basically just an approximate energy cut. And then basically, if there's a muon, we can kind of see it with the outermost PMTs. If they produce hits, it reduces something like 99.5%. We just veto the data for 1.5 milliseconds after So you can do more careful vetoing, but again, this is the quick approach. We don't have time to do some super high level reconstruction. So this is something to get rid of the vast majority of the backgrounds, and we found this works relatively well. Okay, so then just to cover things as well, the more carefully, so this is the slower supernova, the slower pre-supernova. Again, maybe I won't linger on the details, but it's just to say you have a more involved veto strategy for the muons, and then you're reconstructing events. So for supernova events, you can kind of go to a bit lower energies depending on the false alert rate you want to choose. And then pre-supernova events are lower energies, so you have to go to even lower energies. And then you look for coincidences. This time you have time to look for the prompt event, you have time to look for the neutron event, and pair them up and bring down the background, say, a greater deal. But again, when you go to lower energies, you open yourself up to more backgrounds. So these are all considered here from the reactor analysis, but these, yeah, have to be included if you're going to go to lower energies. And so we do that. Okay, so we have all the signal backgrounds, we have the monitors set up, and now we just want to sift through events. There's a few different methods, but I just show here the sliding event method, probably familiar with this, but basically just sifting through events and basically seeing when you have some clustering. And if this kind of rate of a clustering is higher than that would be measured in just background alone, so you can kind of monitor this with time. And you see something that's quite different, then you say, oh, there's maybe a supernova here. So this is the kind of definition just used going forward. Okay, again, maybe more details, but just to say we simulate everything with kind of a full detailed JUNO simulation. We make supernovas from near to far to Earth, and we kind of mix everything together. And then so from here on out, I'm just talking about 4 supernovas mixed in with backgrounds. What was the efficiency that we alerted on them at a certain distance? What's the average distance, say 50% alert efficiency? How far can we go? The alert time when you talk about supernova, how long after the bounce time? And then for the pre-supernova, how long before the collapse do you detect these neutrinos? And the false alert rate, I guess we're familiar with, but here it's just defined to be once per month. And I guess this can be pushed down further, but yeah, just the results here were chosen to be once per month. Okay, so for the fast prompt alert, you can look at the efficiency versus distance. And it's just to say you do really quite well. And depending on the models, the masses, and the hierarchy, and so on, you do something between 200 and 400 kpc. Alert distance wise, which seems pretty good to me. And then alert times, it can really be quite quick. Obviously, the closer, the better, but something on the orders of tens of milliseconds if it's close enough at 10 kpc. And then the estimates right now in terms of actually data transfer and actually shipping this alert along are on the orders of seconds. But yeah, really quite fast. And obviously this has to be tested in commissioning and make sure that this alert can be passed along just okay, but that's what we're doing currently now in commissioning data. For the, say, slightly more careful reconstruction of events, basically you just push your distance a little bit more. You have lower background, so you can push a little bit more. But basically, when you're talking about these distances here, you have a handful of events. So do you see 2 or 3 events? So improving backgrounds in that case, it's mainly statistics limited. So things don't actually change too much. And then there's no alert time here because we just use the quickest prompt alert time as our main alert for now. But there's a few other systems in development. Okay, pre-supernova neutrino or supernova event, you do have to be closer, but again, within the range of around 1 kpc. If there's a supernova within, then we do hope to be able to see these pre-supernova events, which would be quite cool. So if you look at the alert times, these are on the orders of hours. So if you did have an event that was close enough, hopefully you'd see the pre-supernova actually, a great deal of a number of hours if it's close enough before the event. So that would be even more advanced than just measuring the burst of neutrinos, the neutrinos from the burst itself. Okay, directionality in scintillator, typically famously, liquid scintillator detectors sacrifice the directionality you get in Cherenkov. But actually, again, when we're talking about IBD events, the neutrino comes in, the neutron carries most of the momentum information, and you lose it from the positron. So actually, the way to reconstruct the direction is just on a statistical level. So if you collect enough events, you can measure the average displacement of this neutrino compared to the positron, and that kind of gives you an approximate direction. Obviously, this can't really compete with, say, some other direct electron elastic scattering measurements in, say, some other detectors. But again, you have this capability there, so you better be prepared for it. But just to say, this is highly statistics dependent. And so this was calculated, again, maybe a busy plot, but it's just to say the red is, as you'd expect, the further away the supernova is, the fewer events you collect. And then on the right in the blue, you can see the angular resolution, say 1 sigma. And so obviously closer, you can get to better pointing. Pre-supernova is already a bit limited because you have fewer events. But supernova events, again, if it's at 10 kpc, something on the order of around 20, 30 degrees. So decent for a detector that you wouldn't expect to measure any direction in. And so this is a sky map, so some black dots to show some candidate supernova events and so on. And the pre-supernova bands of angular resolution are obviously quite limited, but anything you can kind of give in direction, I believe, is of some use. But obviously, if you use the supernova events where you have, say, more statistics, you can do a decent bit better in terms of limiting the sky coverage. Oh yeah, that's just the values there. But yeah, that's about it. Just to say, the alert system has been established and it's really being tested now. Hopefully in the next month or so, can actually start to be used with the very earliest data. Obviously not so useful, but the detector has to slowly be filled. And we have multiple monitors for different low, high energy and slower analyses for pre-supernova, supernova events. There's the distances, there's the alert times for now, and some modest directionality as well. And so we have more strategies and kind of systems in development, and then also obviously the physics that you can do with these collected events is always being worked on. So hopefully you see and hear these sort of analyses in the near future. But with that, yeah, thanks for listening. Open for questions.
Thank you, Iwan. Are there any comments or questions?
I'll jump in. Maybe you said it and I missed it. What is the expected duty cycle of JUNO? Is it when you turn it on, is it going to be on permanently, or are you planning on science runs with upgrades and taking things down on a regular basis?
It should be on basically permanently, apart from, say, some hours long calibration that we do, I don't know, weekly, monthly, that has to be figured out. Yeah, it should be on pretty much all the time. That's the hope anyway.
Yeah, just maybe to complete, what will not be operating with a 100% duty cycle will be the power plants for the reactor analysis, but the detector will always be on. Any other questions?
Yeah, I'll ask another one. So the plot that you showed of the sensitivity as a function of distance, essentially the detection horizon. Yeah. So, once you get above about 50 kiloparsecs, there's really not much out there in terms of stellar density, right? So one thing that's kind of interesting to look at is to think about what you can see in a galactic supernova, for instance, in terms of different neutrino luminosities and in terms of deep into the cooling tail of the supernova. So, when I look at a plot like this and I see this large detection horizon, I'm like, okay, there's probably not going to be anything at 300 kiloparsecs that's going to blow up. But this kind of sensitivity indicates you could see potentially several seconds or more after core bounce in the neutrinos if the explosion is, in the Milky Way. So I don't know if you want to comment on that, or if you've looked into that, and you see you have some model dependence shown here, but maybe you can comment a little more.
Is this, you talking about the analysis of say the I don't know, the time evolution and so on for an event that's closer is of more interest, I guess.
Yeah, yeah.
Yeah.
That's
I
my
mean,
six.
I guess these things are being worked on. This is mainly just focusing on the alert side of things. But yeah, we certainly hope to record plus minus, minutes from when we alert. So yeah, we just aim to save all this kind of data to disk and yeah. I I see people working on this. I don't work on that, but yeah. Hopefully, yeah, something can come out about that soon enough.
Yep.
Certainly the detector is more capable nearby.
Yeah, actually, since there's no many models that go so long in the cooling as we know in this news and this in these new P models, we haven't looked so much at that. And the major focus for what is the offline analysis has been in the multi-flavor analysis, capturing the most of the proton scattering, lowering the energy threshold. We haven't, yeah. There are not many analyses looking for now at what can be done with the cooling tail. I see a question from Just.
Yeah, speaking of the cooling tail, I will just add that we just have a new beta version of Snoopy out, which includes the cooling tail work by Dalia and Segev. So if you wanted to look into that, that's a good place to start. However, my question was about the this quick and dirty alert here. You said the alert time is on the order of 10 milliseconds. Um, what would that include? Would that just be a yes, there was something, or would that also include a kind of rough millisecond by millisecond event rate?
No, the 10 millisecond is just a 1-0. Did we see something or not? Uh, and then, as I said, actually, you probably, if you had an event that close, then you have to account for just actually passing that information along, through all the systems and then out to, say, other detectors. That would take some time. But the 10 milliseconds shown here is literally Windows moving through events, seeing a burst. Is it confidently above our backgrounds? Yes. Okay. That's an alert. That's what the 10 milliseconds here means.
Can I ask what Juno does plan to send to SNEWS?
I don't know, Martha, is that all figured out? It sounds to me this is
No, I don't think it is figured out.
yeah.
And maybe to complete what Josh was asking, like the kind of available data. So basically, once this very dirty prompt supernova alert is turned on, and then we have a hardware memory that will store 10 seconds of data with a plus minus window around when this prompt monitor has been turned on with a yes. Um, and there basically what we only will have available is what we call the QT pair. So we will not be able to go as far as to full waveform with the very, very, very precise reconstruction, so not 3% energy resolution. But in principle, all the data will be written to disk to later perform anything, and you can bin it and send it immediately in terms of timing. So basically, the timing of the QT pairs, instead of below 1 nanosecond, should be of the order of 10 nanosecond resolution, what you can get in this 10 millisecond window.
But
Yeah,
just
I
to,
will say we have an online event classifier as well. So obviously if you want to do full reconstruction events, it does take longer than
Yeah,
seconds.
yeah.
But we do have an online event classifier with, you can get positions and some simple energies in tens of milliseconds as well. So, obviously it depends how close you are, how overloaded you are with data, but you can get approximate reconstruction. Just if you're asking, is that going to be sent out or not? That has to be clarified and finalized. But we have that at hand. These are options that we have. Yeah.
so just so I understand correctly, what's the amount of time that you can store data?
Uh, Aiming for a minute. I mean, these are we're talking with DAQ people all the time. They're running the systems now with fake data, and the PMTs are coming on, but we're pushing for like a minute or so. If
But
you want to save everything, right?
Yeah.
but it will depend on the distance. You can have a minute at the order of 10, 20 kiloparsec, but if it's Betelgeuse,
Sure.
it will not be the full explosion.
Yeah. But if we're talking just talking with the electronics people, we give a prediction of 10 kpc, that kind of thing, then minute
Yep.
is what we want.
So I see two more questions. Michael?
Yes, you mentioned there's some directional capability, and how soon can you provide this direction estimate?
Yeah, so this was the direction I show here is done with, say, close to full reconstruction. As I said, we have some approximate faster reconstruction that I think can be done on tens of milliseconds. So you could repeat this thing, and maybe it's a bit worse. But actually, the fast reconstruction, it's basically just position reconstruction of two events. The fast one is I don't know, 10s, 20% worse than the full reconstruction. So I don't think these rings will. I'm kind of guessing here. Maybe I shouldn't. I should just go and check this thing fully. But hopefully you could get something a bit worse than this. But again, on the second level.
Thank you.
Yeah, actually, we started doing this comparison of
Oh, cool.
the fast reconstruction and the full detailed reconstruction, and yeah, we should not expect big surprises. So, as he said, it may degrade a little bit, but not significantly, so that you cannot do pointing anymore with the fast one. Because the precise one, the data should be processed within 12 hours delay, so that's really a lot. Yeah, Alec?
Yeah. So one comment is if you buffer the data for a minute-ish anyway, you could also trigger externally on the snooze output, just in case you missed the trigger, but everybody else saw it. And whether that would happen within a minute depends upon how fast everyone else sends an alert, of course, but it can't hurt to try and set that up. Which is the other question in terms of uh, are you or when will you be at the point where you want to try poking with the snooze software? And I'm trying to just, can you send your stuff to snooze? Can you get an alert from snooze and get that, even though you're not going to be capable of Supernova running right away or don't want to, getting the technical bits out of the way and the connections and plumbing done is in advance is helpful. So when might you want to try that?
I can just talk about the schedule. As we know, schedules change, but yeah, hopefully water going into the detector, I don't know, in the next month or so. And then, water filling will take months, say 2, 3 months. Then liquid simulator filling will take half a year. Plus minus any delays there. So I don't know, end of next year, we'd have a full detector, and then backgrounds will be high, things have to calm down. So I don't know, a year. Uh, that's just my personal
Sure. But that, yeah,
view
that
on it.
and schedules are schedules, and they're way
Yeah,
above
yeah,
all of our pay grades, right?
Yeah.
But
yeah.
you don't have to have a functional detector or low noise in order to make sure the plumbing is there and works, though. My point.
Oh, sure. Okay. If it's just starting to all doing the connectivity and stuff, yeah, I'd say you could do it earlier. The point, yeah, we wanted to have everything tested, all our reconstruction, even calibration, deployments, and so on. We're going to be doing as we fill. So that would be closer. That'll be, less than 6 months, say. Uh, uh, if you're just talking about setting up the plumbing, then yeah, you could do it while you filled.
Yeah.
And yeah, you'd have to ignore us, obviously. There'd be lots of spikes and things going on. But yeah,
Yeah,
that's
and you wouldn't even have to send all the crap. You just, does it
sure,
work? Yeah, it worked for today. Great.
sure.
Yeah.
And you happen to have an insider who knows how it all works on the snooze side right here on this call to help you out too.
Oh, cool.
Yeah. So basically, maybe for more completion, the discussion has started with the conveners of the working group that are going to bring it to the EV and IB of JUNO. And hopefully the decision on starting the MOU process and what will be shared when we start the connectivity will be decided during the EB and IB meetings in the next collaboration meeting in January. And in principle, from that meeting, there will be already water going on in the detector. So it's still not the liquid scintillator, but we can also see supernova events in water. So hopefully we will be, yeah, ready by then, and yeah, I know that there are efforts to make this supernova monitor also work in the water phase by adjusting this init cut, so that if something happens, we can also tell, hey, we are seeing something. Okay. Any more comments or questions?
I mean, I have a comment since we're on this particular slide, which is you actually do have a third dimension here, which is the number of neutrinos that you detect. These progenitors are at different distances, and how many events you get gives you some indication of how far away they are. So a combination of event reconstruction, angular resolution, plus that third dimension should allow us to be able to identify these progenitors really pretty quickly. Even JUNO, which has very bad pointing, because you would have that third dimension, and so that would eliminate a lot of potential candidates.
So you just assume a model, but that would be literally instant direction, I guess.
Yeah, so there's a paper by fellow SNEWS, Evan O'Connor, Erin O'Sullivan, and I forget his first name, Segerland, which showed, even if you don't know anything about the star that exploded, you don't know its mass, you can get the distance to a position of about 5%.
Oh, that's nice.
Just from the number of events and all the uncertainty with regard to the flavor oscillations.
Yeah, I mean, 5%, I remember, was kind of the statistical limit. It gets worse when you start including some systematic effects on it, as Iwan mentioned, like model dependency, or even the time uncertainty on where you start counting events to compute the distance.
Yeah.
Yeah, and also like this like probability contour in the sky is not much worse than what we can do even with triangulation. It's of the same order of degrees squared in the sky.
Oh, with the burst, yeah.
Yeah. Okay. Any other comments or questions? Seems no. So yeah, I don't know if in the 10 minutes left there's something else to discuss from this new side.